together. Let me think about this. Where did I write this down? Well, let's be a little informal here and think about what we need to know about the contents of this queue here. If this queue is ever non-empty, what needs to hold of the contents? What we need to remember as an invariant to prove that we have a refinement from here to here? And I'll draw a little arrow over here so we can record an invariant of the queue. Turns out it's okay for the queue to be empty at any time. We might have a mismatch in the rates between these because of the scoreboard or something. If the queue is non-empty, we want to know something about what's in it.
Some kind of well-formed formula for instructions?
Let's see. Okay. Well, it should be a well-formed formula for instructions. Can you elaborate on that?
Well, like some opcodes might require other registers to be 0 or something.
Oh, I see. You're thinking of arcane instruction sets like x86 where not all combinations of operands are legal. We're not worrying about that here. But I think this formulation in Coq is compatible with that. Let's just assume we have a valid decoding algorithm and it only generates legal instruction stuff. Yeah?
So you certainly want to know that that's the result of decoding a segment of what's in the IMAP.
Yeah, so we want to know the fields in there, in the head of the queue, equal the decoding of IMEM. And which address do we expect to decode?
Depending on the PC and because it's 3 states, so minus PCC or plus PCC.
Let's see. I like that minus. I like that minus part because I didn't spell this out here. Decode increments PC every time it runs. But actually, decode owns PC, so there's no one else changing PC. So actually, what's correct here is PC minus 1. And yeah, I'm trying to remember.
What?
Sorry?
Could we have one entry in this queue?
Could we have more than one entry in this queue? I'm trying to remember if we have forced it to be a size 1 queue or something.
I think, like, you mentioned 3-stage pipeline or something.
This is a 3-stage pipeline. 1, 2, 3. Yeah. Somehow the proof works when the invariant only talks about the head of the queue. And that doesn't make sense, does it? Wonder what the reason for that is. I don't know. We'll have to get back to that when we look at the Coq code and see why this works. All right. And the code.
Otherwise, we want something like minus length of this queue, right?
Right. We could have a generalization of this to arbitrary lengths of queues that would subtract larger numbers from PC as we got further into the past or something. And actually, our implementation is pushing the program counter into here also. I'm not sure why that is. It doesn't seem to be needed here. I think that's something you'd use in a more advanced design that involves branch prediction. So it's just kind of along for the ride. So I won't write it on the invariant here. And then, okay, so I think that's really the only invariant that we need. But then we need a rule to reconstruct the state on this side from the state on this side. So that's the register file, instruction memory, data memory, and the PC is still in here. I'll put it here too. So actually, the register file, I think, can be copied over verbatim. Instruction memory, data memory can be copied over verbatim. Scoreboard state doesn't change. The only interesting thing is we have to compute the PC here. And the rule is sometimes, okay, whenever there's an entry in this queue, we have to take the, so that's why the PC is in there. The program counter is in here because if this queue is not empty, the program counter that appears in there needs to be set as the program counter here. Otherwise, if the queue is empty, we take the register value from here. And that's the rule that makes this work. Okay, any questions about that? Those are the two elements, the invariant and the state mapping that we used in our simulation proofs so far. And I'll demonstrate that in Calc shortly. All right, then we have to do the next step here. What invariants do we need to know about this system if we're going to prove that it refines this system? Yes?
Once again, could you please repeat, if we have something in queue, then how do we relate program counters?
The queue entries actually need to include the program counters. I'll write that in here. It's another one of the fields that goes in a queue entry. And then that lets us state the state mapping rule that says, if there's anything in the queue, take its program counter and install it here.
I mean, because in this model, if we only increase program counters, and if we don't have any jumps and things like that, it seems like the program counter, the thing on the right, should be just program counter, the thing on the left minus length of this queue.
That sounds like a generalization of what I said. Yeah, so we could probably simplify what actually goes in the queue by taking advantage of that relationship. So effectively, we add or subtract the length of the queue, something like that. Yeah, that probably works. All right, so what invariant will we need to know here? There's one crucial invariant about the scoreboard. What happens if there's a write queued up in here? What do we expect to be true of the scoreboard with respect to the contents of that write that we find in here?
Should be locked.
Yeah, whenever a register is mentioned here, it should be locked. That's needed to make this correct. I won't write that on the board. And then we need the rules for mapping the state of here to the state of here. Almost all the state elements can be copied over unchanged. There's just one of these that needs a not entirely obvious rule. Which one of these state elements might be different between the two sides?
The scoreboard disappears, right? It's an internal one.
Yeah, that's a cop-out answer. The scoreboard's gone, so before its state is something, after the state is null. True. But how about the ones that are still here?
Register file.
Register file. So what's the state rule for the register file? How do we compute the right-hand side from the left-hand side?
Just apply what's in the right back register.
Yeah, the rule to get this side is to take the state on this side and then apply whatever we find in here. And that's the crucial part of this mapping. All right, I think we're ready to look at the Calc version of all this. Are there any questions first?
Yeah.
Yep.
I have a question.
All right.
Why don't we have like register file to be equal in these two cases? Because in some sense the specification has to stale comparing to the thing it defines. So, I mean, I would expect that in invariant between them we have like the register files are equal, but once they we write something in the left, then we can simulate that in the right. No?
Okay, so the question is, whenever the left-hand side does register write, we should be able to simulate that with the register write on the right-hand side. And why is that not enough to let us avoid this state mapping that has to do some of that work in what seems like a duplicate way? The reason is the actual register write happens at the end of the process here. And we still have to, let's see, what's the right way to put that?
Well, whenever the data memory has been updated, the registers should have been updated in the corresponding way.
That seems like a good way to put it. We have these two elements, the data memory and the registers, that in the spec are changing atomically. And we'll have to do some work to explain why they're not changing atomically here and relate it back to the atomic world. It's an interesting question. Can we somehow put off the data memory change and relate to the after state here instead of the before? But I'm not sure if there's an alternative strategy along those lines. Any other questions? All right, let's move through the code somewhat quickly. So I think I'll just aim to give a tour through the code here so that you can feel empowered to bring up some of these files after class. It's all in the usual repository. Let's start with the spec of our system. Everything here is actually parameterized over the details of the instruction set. Or some of those details. We assume basically 4 kinds of operations: arithmetic, loads, stores, and then a special kind. It's called toHost here, which is, think of it as output. And we assigned a bit pattern to each kind of instruction, but we're not forcing those to be in the actual instruction encoding. It's just a convention internally within our system. And we've also defined internal codes for addition, subtraction, multiplication, and division. And then we require a parameter of the system, which is a function that tells us, well, actually it's a 6 tuple of functions that tells us how to decode from an instruction bit sequence each of those 6 fields represented in our internal encoding. And if you remember some of the details of the FOAS discussion 2 lectures back, you might be able to match the pattern here of quantifying over some type level function that is then used to describe the argument of another function. This is just how we encode a 1-argument function in FOAS. So we require 6 1-argument functions to extract the different fields. And similarly, all the details of running arithmetic are abstracted away in a 3-argument function that takes in the operator code and the operand values. And let's see. Here's our memory. It takes in a structure that has a field isLoad, and if it's a load, then we look up in one cell of the memory and return that. If it's a store, we overwrite a cell of the memory, so a very simple memory. By the way, the exercise I've suggested to go with today's lecture is to prove an optimized version of this memory that introduces a cache of the most recent address you've touched, and prove that for 2 different variants of that, write back and write through, that each of those correctly implements the original memory's behavior. But in the proof here, we'll just change the processor and leave the memory alone. And then, let's see, an example of one rule, the arithmetic rule. Read the program counter, register file, program into local variables. Look up the instruction by dereferencing a cell in the array of the program. Check that when we decode the instruction, it really is an arithmetic operation. If so, then extract the different fields of the instruction, look up in the register file, actually run the arithmetic, overwrite a cell in the register file, increment the PC. And the other parts are pretty similar. I think that's mostly what I want to show. We put the processor specification that I just showed together with the memory. That's the full system. So then we have our actual implementation, which has the register file abstracted into a module. Here's the contents of the records that pass between the decode stage and the execute stage through a FIFO. Fields for op, arith op, source 1, source 2, destination, memory address we're touching, and the program counter. And then the decoder is just reading from the instruction memory, building one of those structs, and pushing it into that queue and incrementing the program counter. Then here comes the scoreboard. It's really just a big array of bits. And the executor has an arith rule that's now different from the one we saw in the spec. We dequeue the description of the instruction. We pull out the op field. We assert that it is an arithmetic instruction. Then we just pull out these other fields of what came out of the queue. And we look up each one in the scoreboard. And we assert that neither one is claimed. So the effect of this, again, is the BlueSpec scheduler promises not to run this rule if any of these asserts would fail. So we'll hold off on this stage whenever some of the resources we need are already claimed. Then we can read from the register file and actually execute the operation. mark the destination register as claimed in the scoreboard, and then NQ the write operation into the FIFO that leads into the next stage. And then I'll just page forward to that stage. It's a really simple one now. It just keeps trying to DQ right into the register file and then remove from the scoreboard. So putting these all together, we have the decoder and the executor and the FIFO between them, the register file, the queue going into the write back itself, the scoreboard. All these get plugged in here. This is our overall implementation. Add in the memory and we have the whole system, not just the processor implementation. All right, and then let's just try to see a few highlights of the proofs. Most of the interesting things happen in these something OK.v files. This is the invariant that we came up with for the first stage, where we are taking the decode and execute and putting them together and talking about what needs to be true of the queue contents between them. This one says whenever there's something in the queue, it's full, then the contents of the PC field of the queue, which happens to be position 7 in a struct, when we add 1 to that, we recover the correct PC value in, I guess that's in the encoder. And this other invariant says when the queue is full, then if we decode the instruction memory at the PC address, we get exactly what we get in fields 1 through 6 of the struct that's in the queue, where each one matches up with the result of some decoding function on the contents of the instruction memory. So I'll put this in one of these funny prop records like below, introducing names for all the registers that should be set, and then asserting these 2 invariants on them. Then I define these proof-specific forward and backward reasoning tactics to plug into the general ones here. We get a not too bad proof of this invariant. We can make this even more automated. It's broken into steps, so you can step through offline and see some of what's happening. We have the register map that shows the program is the same as before. The program counter is, if there's something in the queue, we pull the program counter out of the queue. Otherwise, we use the one in the register. And then we have this proof of refinement, which again, we could make this a one-liner, but it's broken up into steps for educational value here. And then finally, what was the name of that last file? procmemok will show the second state merging. I don't think it'll be too surprising at this point. Here's the invariant for this one. A whole bunch of registers are around, but just one simple property. If the queue is full, then if I look up the register that appears in the queue entry, then it is indeed claimed by the scoreboard. The scoreboard maps it to true. And then I do want to point out again, hey look, that's a pretty short proof that this could be made a one-liner too, but then you wouldn't be able to see all the intermediate steps. Here's the register map, which follows the rule we came up with on the board. As this, the only tricky part is checking if the queue is full and overriding a register if so. Here's the rule map, and then another one of these pretty automated proofs. We can put it all together, prove the processor implementation, implements the processor spec, and then we can trivially lift that to say processor composed with memory implements processor spec composed with memory. And we can extend this final result in the lemma, or the theorem that I've suggested for an exercise today, which is to also substitute in a more optimized memory. Right, so I think that's the end of the right level of detail for these proofs. Any questions here? I do have one announcement that I wanted to more or less end with, so let me bring that up here. So it turns out that you can actually get paid to do this stuff in industry. And there's a startup company called Sci5, which was created by the people who invented the RISC-V instruction set. I'll post this information on Slack also or something like that. And if you think you'd like to work either as an intern or full-time on verifying real processors that are part of a product offering that will help other companies out there build their own custom chips, then please contact this person at this address. And I'm also an advisor for this company, interested in people with COC experience and not necessarily deep hardware experience. I think it's more important to be to be proficient with Coq than to know all this computer architecture stuff. And they have slots for a few more full-time people to work on processor verification there. All right, any last questions? Yeah.